All right, class, welcome to section 2.3. Let's continue our discussion on graphing functions. So as I had mentioned in previous sections, the second derivative also has quite a bit to say about how the graph of the function is going to look like. And I had mentioned when we talked about in 1.5, we talked about higher order derivatives. So I did mention what a second derivative would do to a function. So I even graphed this function, or this type of function, I should say, right here. Let me just draw it. I don't know why this comes up dotted, but here it is. Here's a function, yes. And both of these functions right here, as a matter of fact, are increasing functions. So let's say I'm looking at this function f of x, looking at this function f of x. Both these functions are increasing, right? They're going up. So we definitely know that their derivative is going to be positive. However, so see the tangent line, the slope of the tangent line here is positive, right? So that simply means the derivative is positive. The same thing here. This tangent line has a positive slope. That means that the derivative, the first derivative, is positive, right? So greater than 0. However, these two graphs look different from each other or increase differently. And what makes them increase differently is really hidden in the second derivative clue. Look at this tangent line and look at the next tangent line. What can you tell me about the slopes of these tangent lines? Or even if I pick one before, here's a tangent line, there's a tangent line, there's a tangent line. What happens to these slopes? This slope here might be maybe a 2. This might be a 1. This is only a half. So what I'm telling you here is that the slopes are decreasing. They're getting lower and lower and lower, right? Okay. So if the slopes are decreasing, that means the first derivatives are decreasing, or is decreasing, let's just say. And we've learned in section 2.1 that if a function is decreasing, that simply means its derivative. So what's the derivative of the first derivative? Well, that's the second derivative. That simply means that its derivative is negative. Yes, so function's decreasing, that means its derivative is negative. So there you go. Let me go on to this picture here. What happens to these tangent lines? Or I should say the slopes of these tangent lines. This might be a 1/3, this might be a 1, this might be a 2, right? 2.5 and so on and so on. So these slopes are increasing. They're getting larger in value. That simply means, what is the slope of the tangent line giving me? The derivative, yes? So again, if a function is increasing, that means its derivative, yes, so that means the second derivative is positive. Okay, so we have names for a graph being turned this way or turned the other way. We call that concavity, okay? So concavity is telling us how a graph is turning. So this one is definitely concave down. The graph is turning down. And this one here is definitely concave up. So just to give you another graph with more, look at this. Concave up, right? Just like here, it's turned up, yes? So again, think about the slopes of these tangent lines. That might be a -2. This might be a -1, -0.5, 0, 0.5, 1, 2, right? So as you see, the slopes of these tangent lines are getting larger and larger, yes? And then what happens here? So again, the slopes are increasing. That means the second derivative is positive, right? The derivative of this first derivative. And then what happens to the slopes? They're slowing down, right? From the 2, it might just be a 1, it might be a half, it might be a 0, -0.5, -1, right? So the graph is turning down. The derivative of the first derivative is negative, yes? And then back up. Okay, concave up. So One way of remembering this on concavity, I'm going to draw this one more time for you. Well, I'll just put it here. Is this is definitely concave up. And we're going to just write CU for concave up. Now, to remember that something or a graph is concave up, it's simply, you think about it, is that it holds water. And you see it's turning up, right? Now, another way of remembering, that's my favorite, is that a concave up graph is a smiley face, right? So again, concave up means that the second derivative is positive. So positive, smiley face, yes? Now, negative second derivative, your graph is concave down, you're forming a sad face, right? Second derivative is going to be a negative, a sad face, right? And there you go. So doesn't hold water. Okay, so one more time. The second derivative tells us about the concavity of the graph. So if the graph is turning up, right, holding water, smiley face, yes. Positive second derivative is, if the second derivative is negative, you have a sad face. The graph is concave down, yes, it doesn't hold water. So one more time, where the second derivative is positive, yes, the graph is concave up. Yes, so one more time, smiley face. Ta-da! Not good at drawing, yes, but there it is. There's a smiley face for you, okay? So what we say is that the function is increasing at an increasing rate. So the rate of increase is also increasing. And then the second derivative is negative. On an interval, we say the graph is concave down. In other words, the function is increasing at a decreasing rate. So the rate is decreasing, the second derivative is negative, sad face. Okay, there it is. That's what it means. Okay, now, just before we move on, and I'll mention this next, what are we going to be looking for? Okay, up, down, up, down. What's going to matter is these points where it's going to start changing. Yes, so these points are going, it's the same thing as the minimums and the maximums from before, right? A maximum is where a function changes from increasing to decreasing. Yes, a minimum point is where a function changes from decreasing to increasing. An inflection point, I'm defining them on the next page, is where the concavity of the graph is changing. So inflection points. Okay. So just as I said, an inflection point is a point on a graph where the concavity of the function changes, right? From concave up to down or concave down to up. Okay, so the second derivative will change signs. Okay, so which ones in this list of points here, which I'm drawing back again from, or I'm bringing back again from 2.1, it's the same graph. Which one do you think are inflection points? Where does the concavity change? Well, it looks to me, first of all, that the graph is concave up here, right? Up to this point, yes? Then the graph is concave down. Up to where does it look down? Up to here, but then it's still concave down all the way up to here, and then it's changing to concave up. So of these points, which ones do you think are your inflection points? Okay. So if you answered B, and G, you are correct. These are the only points where the concavity has changed. Now what about E? E is not an inflection point. Why? Even though it's a funny point on a graph, the graph doesn't change concavity. It's still going from concave down to concave down, from a negative second derivative, yes, to also a negative second derivative, yes. So as we saw in 2.1, we had what we call the critical numbers or the critical points, but not every single critical point led to a minimum or a maximum. So the same thing here. Something's going to happen at E, but it's not an inflection point, right? So only where the second derivative changed signs, right? So what is the sign of the second derivative? The second derivative here is a positive smiley face. The second derivative here is a negative sad face. The second derivative here is a negative sad face. Up here, the second, or from here on out, right? The second derivative is a positive. So it changed from plus to minus and minus to plus at B and G. Okay? All right. So, which ones are our critical points? Let me remind you. The critical points in our graph were where the what? The first derivative was equal to 0 or it was undefined. So the second derivative, the critical points is where we find possible mins and maximums, yes? And to find our mins and maximums, we looked at where the second derivative was 0 or undefined. So let's review that. Where was the second derivative equal to 0? The second derivative is 0 here at, okay, I'll make it blue. Here at A. The second derivative is 0 at C. The second derivative is 0 at F. And the second derivative is 0 in H. What happens at E? The second derivative is undefined. Okay, so why? Because there's a corner point, right? Where there's a corner in the graph, there's no derivative. So the derivative is undefined. Sure enough, all of these are min, max, min, right? So you find your mins and maximums amongst your critical points. Okay, so the same thing we will do to find an inflection point. Where do we find an inflection point? Is about the second derivative. So we'll find an inflection point where the second derivative is either 0 or undefined. Yes. Now, I'm just gonna, because this is actually not quite true, just because, again, we will find, I'm just gonna say something. Our inflection points amongst the points where the second derivative is 0 or it's undefined, yes, but not every point in question will be an inflection point. So what I mean by that is just because the second derivative is 0 or undefined, it doesn't mean that you found an inflection point. What's an inflection point? An inflection point, what also has to happen is that the second derivative has to change sign. So as you see, E is one of these where the second derivative is equal to 0 undefined. Why? Because what happens at E? The first derivative is undefined, yes? The first derivative is undefined, yes? As I had already mentioned, if one of a function, right, or derivative, or at any point, any function, yes, this first derivative is a function itself. if the function's undefined, any derivative after that is undefined. So if the first derivative is undefined, then its derivative is undefined, then its derivative is undefined, and so on and so on. So the second derivative is undefined at e, yet the function didn't change concavities, right? So the second derivative didn't change signs. It stayed from negative to negative. So let me give you an example of a graph where this would happen. Here it is. So I'm going to put this one more time. To have an inflection point, the second derivative must change signs. Yes. Left and right of it. Yes. So here it is. Here's a graph of a function. What happens here? Now, at this point right here, there's a vertical tangent line. Yes. So at this point right here, the first derivative is undefined. So if the first derivative is undefined, that means what? The second derivative is undefined. Yes. So as you see, at this point here, there's no min or max, right? So it is one of our critical points. Yes. So it's no min or max, but is this an inflection point, right? The second derivative is undefined, so it possibly could turn into an inflection point. What happens to the concavity? It's concave up left to right, and then it's concave down afterwards. So yes, this is an inflection point, right? Because we're changing from up to down, okay? Now, in this case, like that problem E there, or that point E, this is what happens, right? At this point here, the first derivative is undefined because you're coming to a corner. So also it means the second derivative is undefined. Yes. So its derivative is undefined. Now, do we change concavity? It's going from concave down, looking down. That's concave down. So that means what? This is not an inflection point. Okay. All right. But the point is, just like, so we don't quite have a name where we say it's a critical number, and amongst the critical numbers we have mins and maximums. Unfortunately, well, I don't know if you want to call them critical numbers, that's fine. But the point is, if you want to find an inflection point, I'm just going to call it an inflection point. I'm going to write it here. If what? The second derivative also changes signs. So all three have to be satisfied. Either 0 undefined, that's where you're looking for. If the second derivative changes signs left and right, then you got yourself an inflection point. Okay, so find, let's just say, possible inflection points. So how do I find possible inflection points? I'm going to find the second derivative and look at where it might be 0 or undefined. Okay, so let's find the first derivative first. So that's a 3x squared minus 2x and minus 1. Okay, again, with the first derivative, you're doing things. We're going to do that in a bit. But what I want to do is just find those possible inflection points. So it's about the second derivative. So that's a 6x minus 2. Now, that's never going to be undefined again. Why? It's not a fraction where the denominator could be 0, but can this second derivative be 0? Sure enough, where? When x is equal to 1/3. Yes, but again, remember, so possibly, and yes, we will have an inflection point at 1/3. So that's the x coordinate. How do I find the point, right? The y coordinate to it? Plug this x back into the function. Yes, that's the inflection point of the function, not of the derivative, not of the second derivative, yes, of the function. So you'll need a 1/3 cubed minus 1/3 squared minus 1/3 and then plus 2. So I already did the math on this somewhere. No, I did not. whatever it is. Okay, so 1 over 27, I have to do this. 1 over 9 minus 1/3 plus 2. Why am I doing this? You guys can put it in, fine. 1 over 27 minus 3 over 27 minus 9 over 27 plus 54 over 27. So 55 minus 12 is 43 over 27. There you go. All right, did the math. Faster than putting in the calculator. Okay, let's try this one more time. How do I find a possible inflection point? I'm going to look at where the derivative is 0 or undefined. Yes? So, get to work yourselves. See if we have matching answers. And see who gets there first. So, here it is. First derivative. Find the second derivative. Okay. Set it equal to 0. Again, this could not be undefined. Okay. So I'm going to get a 12x squared is 16, divide by 12. And that reduces to 4/3. Take the square root on both sides. And by the way, remember the square root property? We have to put a plus or a minus, so I'm going to get 2 answers, yes? And so which ones are my inflection points? One possible one is plug in 2 over the square root of 3 into this function, which I'm in no mood for, whatever that is. And then the same thing for negative 2 over the square root of 3. Plug it into your function, right? This one right here. All right, so yeah. The point is, we better just do the whole thing. So what do I mean the whole thing? We already took our graphs, and now we're just going to continue. So we already took the graphs to where? Find the first derivative, make a sign diagram, right? And then we graphed some points, or we plotted some points, and then we graphed the function. I said, what would be in 2.1 and 2.2? So I said, what would be more helpful is if we could also use the second derivative. So I purposely am going back to one of the problems we did in 2.1, and you might remember or not, but when we solved this problem, I said, once we have the second derivative on our side, it will be even more clear why the graph has to bend a certain way. So I'm going to do this whole problem one more time again. So we're going to make a sign diagram for the first and a sign diagram for the second derivative. They work the same way. So I'm going to get started with what? The first derivative. We already practiced on this. What we're doing is just continuing our discussion. Okay, so the first derivative, what is it? 2/3 x plus 3 to the 1 less than 2/3 is negative 1/3. Remember this problem? And then the negative 5 goes to 0. So as always, if you have a negative exponent, make it back positive by throwing the x plus 3 back on the bottom. So can this first derivative, let's find the critical numbers next, yes? So to find a critical number, we're looking at when is the first derivative equal to 0? Well, the first derivative can never equal to 0. Why? Because as I keep telling you, a fraction can only equals to 0 if the top is 0, and the top is 2, and 2 is 2. But the second choice we have is, can the first derivative be undefined? Yes. When is the first derivative undefined? If the bottom is 0, right? So, again, just to put it clear, okay? We've done this a few times already. Oops. So when is the bottom 0? I keep always wanting to say the bottom cannot be 0, sure enough. But if it's 0, it makes the derivative undefined. So when is this 0? If x is negative 3. So this is a critical number. Okay. Now let's make a sign diagram. So from negative infinity to positive infinity, negative 3 is my only critical number. What happens at negative 3? The first derivative is undefined, yes? However, what are the signs left and right of it? So if I plug in a number, let's say, to the right of negative 3, let's say 0, yes? So I'm plugging in 0 as my test point. If I plug in a 0, I'm going to get 2 over 3 times the cube root of 3. The cube root of 3 is a positive, times everything else. Those are going to be positive, yes? If you plug in a number less than negative 3, let's say negative 4, that makes it a negative 1 here. Cube root of negative 1 is a negative, right? Times all these positives, that makes it a negative. Now, what does that mean about my function itself? That simply means that the function is going to go down, right? It's decreasing, then it's going to be increasing. Okay. So that's my first derivative sine diagram. All right, let's move on and find that second derivative and make its sine diagram. So I'm going to take this version of it because it's much easier. So it's going to be a negative 2/3 times the negative 1/3 down, right? So I'm taking the derivative of this. So it's 2/3 times the negative 1/3 that comes down, that's negative 2/9, yes? Then x plus 3 to the 1 less than negative 1/3, that is negative 4/3. So let's make this here, I'll even do that. Okay, so I have a negative 2, yes, over 9. The negative exponent makes this go in the bottom, yes. So what is the 4/3 exponent? It's a cube root, right, of x plus 3 to the 4th, right? So when I make my sine diagram, I'm going to show you, okay, so one more time, where are the possible inflection points? Again, the second derivative is never going to be 0. Why? Because the top is not going to be 0. But the second derivative is going to be undefined at the same place where the first derivative was undefined. Remember what I said? When one fails, all the other ones afterwards are going to fail. And I'll clearly see that this fraction will become 0 if x is negative 3. So let me make a sine diagram for this. X, f second derivative of x, and then f of x. So it's a sine diagram for the second derivative. Okay. So from negative infinity to positive infinity, negative 3 is where things are happening. The second derivative is undefined there, right? What about the signs? So again, pick any value, really, it doesn't matter what you pick, and to plug into this second derivative function. If I put in a 0, 0 to the 4th, 3 to the 4th is positive, cube root of that is positive, positive. With the negative up front, that makes it a negative. Even if I pick a negative 4 plus 3 is negative 1. But raised to the 4th power, that's a positive 1, right? Cube root of positive 1 is 1 times 9, and the negative 2, that makes it a negative. So what does that mean for the function itself? Negative second derivative, that means the function's going to have a sad face. So it's going to be concave down, and then concave down again. So negative 3 is not an inflection point because the sign of the second derivative didn't change, right? So it stays concave down. And now if you remember, from our graph, we already graphed this one, but I said it gives us an extra clue. So negative 3 really is the only point of interest here in this function. If I plug in a -3 into this function, that makes it a 0 to the 2/3 is 0. 0 minus 5 is -5. So really I only have one point of interest, which is -3, -5. So what happens to my graph with left and right of this point? So we could tell from the first derivative that what? The graph is coming down, yes? And then it's going to go up. But it can go up different ways, right? It can come down different ways, yes? But we know how it's coming down. It has to be turned down the whole time. So in other words, what? It comes down, turned down, right? Concave down. And then it's going to be increasing, right? Right here it's increasing. But it still has to be turned down. So there's your graph, right? We already guessed that because we knew it has to come to a corner point, and if we turn it the other way, it would mean that we would have a nice horizontal tangent line, which we don't because the derivative is undefined. Okay, so we're gonna do a whole lot more problems, putting it all together in the next video.